Hi, I'm TJ Rowe. You've seen me in such fine quality, epic chemistry educational videos such as Max and Acids, The Connection, and PCs are a salt, or are they salty? Part 2. Alright, this is our last chapter together for AP Chemistry. After that we'll talk a little bit about electron spectroscopy, but for now this is Electrochemistry, chapter 18. So during this video you'll probably want to pay attention to some of the things I'm going to tell you to write down, because that way I know you in fact did pay attention to the video. Alright, so this is dealing with electrochemistry, and before you have got two solutions with the salt bridge. We got a little voltage indicator there, and we have the anode and the cathode and all that. So let's dig in. Let's dig into this. Because really, you think about it, it's an application of redox. Okay? So if we look at zinc and copper, if we stick a zinc rod into a copper solution, you can look in the next picture and you kind of notice, hey, wait a minute, this thing is, whoa, hey, what's happened with the zinc rod? Well, the zinc rod is actually being eaten away, it's being slowly dissolved, and you got a precipitation of copper down below. What's going on? Well, this would be an example of a redox reaction. Somebody is taking and somebody's losing. So what is exactly electrochemistry? Well, you have to think about it. It's the interchange of the chemical and electrical energy. Now, there are two processes that involve the redox. You are generating an electric current from a spontaneous chemical reaction. Now, remember, spontaneous, delta G needs to be negative in order to get that spontaneous chemical reaction. Now, on the other side of the coin, there is the opposite process where we need to use a current in order to make a chemical change happen. Now guess what? That's non-spontaneous. So that would be a positive delta G. So let's do a quick review here about redox. Okay? So oxidation reduction reactions involve a transfer of electrons. Somebody is gaining electrons and others are losing it. Oh, wow, like some of our presidential candidates who've quit this 2016 race. So there's two ways to remember about oxidation reduction. The first one that I remember was Leo the lion goes grr. As you can see there in our thing there. Lose electrons, oxidation, that's Leo. Gain electrons is reduction, that's the grr part. Then you have oil rig, where oxidation is loss and reduction is gain. That's a tough one. So now we know that what oxidation and reduction are. We got to talk about the agent, the oxidizing agent and the reducing agent, because that can be a little bit confusing. Okay? So the oxidizing agent is what takes electrons from another species and thus itself is reduced. Okay? You could look upon that as an oxidizer. It takes electrons from another species and thus itself is reduced. Oxygen is a pretty good one because it likes to take electrons, but chlorine does too. Okay? So an oxidizing agent takes electrons from another species and gets reduced because it gains electrons in the process. If we look at the reducing agent for a moment, it gives electrons to another species and thus itself is oxidized. So reducing agent is the loser. It is the Leo, okay, where the oxidizing agent is the grr, because the reducing agent gives electrons. So it's losing electrons to another species and thus becomes oxidized. Okay? Moving on. So some great oxidizing agent examples there you can see. You can check out oxygen, ozone, fluorine, chlorine. Oh, hey, I already mentioned some of those to you. Hypochlorite, which you will find as a big ingredient in bleach. Okay, nitric acid. Oh, yeah. So you can look here on the agent, and then you can look at the products there. So those are great oxidizing agents. Reducing agents would include things like sulfite compounds, okay, and ascorbic acid. Ascorbic acid, most people would know that as vitamin C. You might want to write the word vitamin C on the right-hand side of your paper where the lines are in your notes. That would probably be a good one right there. Phosphites, hypophosphites, and phosphorus acids. Those are also great reducing agents. Okay? Compounds containing the Fe2 plus ion like iron 2 sulfate. Carbon monoxide is another one. And good old carbon, because it's a reducing agent as well. Woo, man. So we have some oxidizing agents, which are perfectly reduced because they gain electrons. And then you have got reducing agents, which are perfect for oxidizing because they lose electrons. Let's talk about applications here, shall we? Which gets to the center point about this chapter. Whew, yeah, let's take a look over here. So moving electrons, that's the electric current. That's where the zzz comes in. All right. So let's take a look at an example here. We look at 8 hydrogens plus MnO4 minus plus 5 Fe with a plus 2 plus 5 electrons gets us an Mn, manganese, with a plus 2 charge, or manganese 2, 5 irons with a plus 3 charge, and we end up getting water in the process. What in the world's going on? Well, if we look at a chemical reaction and we're looking at the electrochemical parts of it, probably for us it'd be a fantastic idea to break those reactions into half reactions. By doing that, guys, it allows us to understand some things. So here we look at the oxygen, the hydrogen, and the manganese. That's one half reaction. So we have 8H plus, earthquake, MnO4 minus plus 5 electrons, and you get Mn plus 2 with 4 waters added to it. Okay? So that's one half reaction. Now we have the other half reaction where we've got our 5 with the Fe plus 2 becoming an Fe plus 3 and the electrons to go with it. So the electron that goes with it. So wow, what happened to the iron? Was it reduced or was it oxidized? Well, if you look Leo the Lion Goes Grr or oil rig, you'd notice, hey, the iron lost electrons, and therefore it was oxidized, which that makes it a reducing agent. Possible! So, in the same mixture, it happens without doing useful work, which is true. If you dump this all into a beaker, yay, we get the chemical reaction, but is that going to be practical for us? Really? No. No, it's not. But what if we can sit there and put it into 2 separate beakers, and we were able to connect a wire in between them? So on the beaker on the left, we have our MnO4 minus, our H plus, and on the right-hand side, we got our Fe2 plus. So, connected this way, we can get the reactants to start. The reaction starts, and the idea is that our reactants will collide. Okay? Now, here comes the problem, though. It's not going to last very long because the opposite charges are building up. Wait, what are you talking about? If you try to run this reaction to completion, you are going to have a bunch of electrons on one side and nothing on the other side. That's the problem. In order to make the electricity flow, it's got to keep flowing in order to make things happen. And at this point right now, if we look at what we've got, this is not working. So it stops immediately because you're just going to end up with all the electrons on one side. Okay, it's like taking the electricity and you put it into one thing and that's the end of it. You're not getting anything else with it. The reaction stops immediately because of that buildup. Okay, here's the thing. You're not going to get any useful chemical energy and you're going to be getting heat from this. Well, wait a minute. Where's the heat coming from? Well, remember, you're tearing apart things. You're causing the iron to lose electrons. And look at things, see that previous reaction there.
Okay? This is pretty huge. So we're getting heat, but we can't use the heat. But we do have useful chemical energy. That's exciting, but we can't use it. So there's our reaction if we look at it. We got our H plus and our MnO4. We've got our 5 irons over here with our 5 electrons. Okay, so what's going on? Well, what happens is the electrons are going over to the other side, and then it piles up, and then that's it. The reaction stops because there's no new territory. So there has to be something that goes into a cycle in order to keep the process going, at least for a longer term than just a second or two. Okay? So let's talk about the idea of a basic galvanic cell. This is the basic idea behind a battery. You have an oxidizing agent here. You have a reducing agent there. You have the anode and the cathode. Now this would match with the positive and negative terminals of a battery. Okay? And remember how important it is when you deal with a battery, you are dealing with the same basic idea. You have a reducing agent and an oxidizing agent. You have a cathode, you have an anode. Now in between there needs to be some kind of a connection between the two beakers of solution. Now there's a couple of ways you can do this. One, you can do what you see here on the left-hand side. You see a little canal, a little opening there, and you have got a porous disc there. Okay, well, porous means full of holes. So that means some of the stuff is able to get through. We'll talk about that later. Now, on the other side, you have what's called a salt bridge. Typically, it's potassium nitrate, okay, and that also allows the flow of things to go through. But like I said, we're going to get into that in a moment, maybe. Okay, so here we go. We use our salt bridge, and it allows the current to flow. Okay, well, what do you mean? What are you talking about, the current? Electricity. That would be kind of important because remember, if it's flowing one way, it stops. There has to be some kind of a cycle that's involved here. So, what do we've got? Electricity would be traveling in a complete circuit, which is what you would expect whether you're working with something that's battery operated or you're plugging something into the outlet. There has to be a complete circuit. It can't go one way because then all the electrons are stuck in that one place and you're not getting any flow, you're not getting any reaction, and you're going to look stupid in front of all your friends. So, there is another option that we have. We could use a salt bridge, but there's something else that we could use. A porous disc, which again allows ions to flow without a lot of mixing of solutions. Now that's a pretty important idea because remember, if the solutions mix, it's not going to work. It'll work a little bit of time, but that's about it. Okay? So that's not going to work out very well for us. So that's why we have a porous disc, allows a little bit of mixing. You need that, a little bit of the mixing, in order to make the flow happen. Okay, so now here we are. We've got our two beakers basically. We've got a wire. We've got a wire there, and if you notice, here's your reducing agent. Remember, it loses electrons, so it's being oxidized. And you got the electrons. You can trace the path of the electrons there. Okay, and it goes through to the other side. So it goes from the anode to the cathode. So when you're trying to identify, hey, what is your anode and cathode on a battery, remember, it's going from the negative to the positive. So the cathode's your positive side of the battery. Okay, you'd say, well, why positive? Well, what do you think electrons are? Electrons are negatively charged. They're going to be attracted to the positive side. Yeah, it's a good thing. Okay, they're going to leave the negative side. They're going to leave the anode, and as that reaction continues forth. So you guys need to memorize this. I think this will help you so much. Cathode reduction occurs. That's what we call the red cat. Okay, there's the red cat there. That's a cathode reduction. Okay, anode is oxidation. Okay, anox. We have an ox right here. So the red cat and the ox, anox, will help you. Oxidation, loss of electrons. Reduction, gaining of electrons. Oxidizing agent, substance being reduced at the cathode. In other words, it's picking up electrons. Okay, the reducing agent is the substance being oxidized or losing electrons at the anode.